Any general questions, problems, anything? Um, Reminder of sorts. Technically, sprint 4 is due this week. I did open the drop boxes for it a few minutes ago, so anything? Okay. This week is really the end of equilibrium. And of course, as I always say, all equilibrium problems have 3 parts. Still true. And as I've been saying for some of these special cases, they're just special cases because there's something about unique to that particular type of reaction. So, for example, when we're talking about acids and bases, the issue is pH, right, which only really pops up there. And so it changes a little bit the way we think about those problems, but in the end, they all can be solved with a balanced equation, a nice chart, and a K equation. That is still mostly true for our last little equilibrium type. But of all my special types, KSP is most special, as you'll see in a minute, and to some extent causes the most confusion. I've also said, and also still true, that a lot of Chem 2 is correcting the oversimplifications from high school and even sadly to some extent from Chem 1. And this little equilibrium also corrects a bit of an oversimplification, in this case related to solubility. Right, our last little equilibrium is what's known as a KSP. Right, again, the subscript changes nothing. It's just telling me what the reaction type is. Right, and it really corrects the basic issue of solubility, which up till now has been, as I've been saying, oversimplified. Right, and by that I mean, right, we've been talking about solubility as though it's binary, right? Something's either soluble or insoluble, right? Generally speaking, that's really not the case, right? Solubility is actually an equilibrium, and what we've been referring to as soluble or insoluble are just the extreme cases of the equilibrium. Something that's soluble has essentially a really high equilibrium constant. Something that's insoluble has either a very low or a 0 equilibrium constant, right? And for some compounds, right, this works fairly well, which is why we use it, right? More generically, in the middle, where it's a little bit soluble, right, we'd have to solve it as the equilibrium problem sometimes, right? And the sometimes boils down to what solubility actually is, right? It's the maximum amount of a compound that can dissolve in water, right? And emphasis mine on the maximum, right? Because the one really special feature about KSP, right, revolves around the issue of maximum. It is still fundamentally an equilibrium problem, which means it still fundamentally has 3 parts, right? And so if I'm talking about something like iron carbonate, my reaction is really the dissolving of the iron carbonate salt in water. right? And so if I were to write it out as a balanced chemical equation, even though it's mostly a physical change, right? I've dissolved it. I haven't really done any fancy chemistry here, although since it's an ionic compound and dissolving ionic compounds dissociates them, in some sense, I have broken a bond, the ionic bond. Right. You'll notice right off the bat, I have hidden water, right? By which I mean the water itself is not participating in the reaction, but since this is a dissolving reaction, right, I'm going from being solid iron carbonate to aqueous ions. And so there is water there, but I do not include the water as part of the balanced equation because it's not participating in the reaction itself. It's just the solvent. And so, right, balanced equation gives rise to a K equation, gives rise to an ice chart. The K equation is really what fundamentally ends up making my KSPs special, right? Because, of course, since the solid is a solid, it has a constant activity of 1 and therefore does not appear in the K equation. Right. Now, you might say, okay, great, big deal. And I would tend to agree with you, right? Because, of course, as I'm fond of saying, all my equilibrium problems have 3 parts. I like that. I stick to that. I trust in that, right? And so this just happens to be my K part for this particular equilibrium, right? And to some extent, that's true, right? Except here's the thing. My K equation has no reactants. I mean, technically, it's there as an activity of 1, right? But it does not depend in any way on the concentration of the iron carbonate. And so, in some sense, my K does not know how much iron carbonate is there, right? It doesn't care. There could be a whole lot of iron carbonate. There could be very little iron carbonate. It doesn't affect the equilibrium because the equilibrium is solely determined by the concentration of the product ions. Okay. Now, again, you might still be saying, well, big deal, who cares? Well, I don't have to care a lot, except because it can't tell anything about the reactants, this is really the first equilibrium we've seen that does not have to be satisfied, right? By which I mean, if you take a normal equilibrium, you know, like my Ka, right? When in doubt, go back to acetic acid. Right. Right. Like virtually every equilibrium we've seen up till now, right? It has both the products and the reactants represented, which means if you throw acetic acid in water, no matter how little or how much it gets to equilibrium, because the equilibrium essentially is defined by the ratio of the products and reactants. So if you throw a whole lot of acetic acid in water, right, it'll dissociate as much as it needs to get that ratio to the magic number. If you throw a very little bit of acetic acid in water, it'll dissociate however much it needs to get to that ratio, right? For my KSP, there's no ratio. There's just the products, right? And so when I have the ratio of products and reactants, I can always either end up with very little products or a whole lot of products, right? Or very little reactants and a whole lot of reactants, whatever it takes to get me there. But because the reactants aren't part of my equilibrium, right? If I dump a whole lot of iron carbonate into water, right, it can dissociate its way to equilibrium, but that equilibrium only depends on the iron and the carbonate concentration. And if I dump very little iron carbonate into water, it'll dissociate, but it can't necessarily get to equilibrium, right? Because if I use a random number, right, if this is 9, well, the only way to get to equilibrium is 3 and 3, right? So if I were to make 3 molar iron carbonate solid, it dissociates, I get 3 molar of each ion, right? And I'm at equilibrium. But what if I start with 2 molar? The most I can get is 2 molar and 2 molar. 2 times 2 is only 4. There's no way to get to 9. Right? That never happens with the acetic acid because you can always see how much acetic acid is left. It's in the denominator of the K, right? And so, you know, if there were iron carbonate here, I would always be able to get to equilibrium because this would be a ratio. And so I would just have a wee little bit of iron carbonate left, which would make my ratio 9. But there's no denominator. And so little bit or a lot of iron carbonate doesn't change anything because it's not part of the equilibrium, which means you have the somewhat unusual, at least for us, right, condition that I don't have to get to equilibrium. That has never been the case before. Hence, right, my emphasis on the word maximum. Right. In a very real way, right, this is not so much an equilibrium as it is a single value, right, if I'm dissolving something, right. In the case of my recently manufactured example, right, if this were really 9, right, then 3 molar is the maximum solubility of the iron carbonate solid, right? But in a different way, it's also the minimum amount that gets me to equilibrium, right? I can't throw in 1 molar iron carbonate and get to equilibrium, right? And so it is very much a single value if I'm talking about solubility.
Is equilibrium in this case then just like a saturated solution?
What's that?
Is equilibrium in this case just a saturated solution?
Equilibrium in this case is, yes, just a saturated solution. right? And so that is, in some sense, the very special feature that KSP has. It's the only equilibrium we've seen that isn't always in play, right? This doesn't change a lot, right? I mean, it's still balanced equation, equilibrium, constant, ice chart, and solve, except I have to sort of add a fourth step, which is see if the equilibrium applies at all, which we'll talk about in a minute, right? Because this equilibrium constant is just the product of the soluble ions, it is called a solubility product, which is what the SP was for in my KSP. Right. And some of this is sadly easy and sadly boring, and frankly doesn't tell me anything that Wikipedia doesn't, right? For example, if I use real numbers instead of my made up 9, right? The KSP of iron carbonate is known. Somebody measured it. It's in a different appendix in the back of your book, right after the KAs and the KBs, right? And it turns out in water, the KSP of iron 2 carbonate is 3.07 times 10 to the minus 11, right? And so if I am to actually be at equilibrium, I have to achieve that value, right? And so balanced equation, ice chart, K equation, and solve. Right. I somewhat jokingly, right, put a tiny, tiny bit of equilibrium iron carbonate there. My point being that, right, if I start with less iron carbonate than the solubility, I can't get to equilibrium, right? In this case, since I'm looking for how much gets me to equilibrium, I'm always going to get there. In some sense, what I'm really looking for is S, which is the solubility. It's the amount of iron carbonate that will dissociate to get me to equilibrium. But, you know, it's really only the right side of my ice chart that matters. So it's a 1-to-1 salt, so plus X and plus X, right? The KSP is just the iron times the carbonate, which is just X squared. And so in this case, X is just the square root of the KSP, which is 5.54 times 10 to the minus 6, which is technically S. Right. And that by itself is true. I also want to say that by itself is somewhat boring in the sense that it does not change. Right. If the question is what's the solubility of iron 2 carbonate, the answer is always 5.54 times 10 to the minus 6. Right. To that end, if I'm talking about solubility, why wouldn't I just quote the molarity? Why start with the KSP and make you solve it? That's an excellent question. And there's no good reason for it, which is why if you go to Wikipedia and you look up your average salt, they quote a solubility, but they don't typically quote a KSP, right? Far more common, if you go to Wikipedia, is it has something like grams per milliliter or grams per 100 milliliters or grams per liter or possibly molarity. But again, this is chemistry specific, whereas the grams per liter, right, is more generic, right? It's the number of grams of the salt that will dissolve in a given amount of the water, right? And if I quote that number, I'm essentially quoting the solution to my KSP problem. But since that number is not going to change, there's not a lot of point in solving my KSP problem every time I considering the solubility of some salt. What I want to know is how much can I dissolve, right? And for pure water, that number doesn't change. Right. And so the solubility problem, which is what this is, right, is really not the KSP problem we ultimately want to solve. Right? If my question is what's the solubility, it's frankly much easier just to look up the solubility. Right? Whether I start with the KSP or I start with the solubility, it's a single number. It's the maximum amount that will dissolve. There's no point in solving the K equation when my solution to the K equation is never going to change. Right. To Quinn's point, yes, all equilibria are temperature dependent. More on that either the end of the week or next week. So, of course, solubility being just another equilibrium is temperature dependent. Right. I should mention, since we've been doing Ks and KBs for a while, right, KSP is the return of stoichiometry, right, by which I mean everything is not 1-to-1-to-1 anymore. And so again, if I ask the same question about good old barium phosphate, right, again, the KSP from the back of the book in the appendix where such things are found, right, the KSP for barium phosphate is 6 times 10 to the minus 39, right? Like any other equilibrium problem, balanced equation, K equation, ice chart, and solve, right? The balanced equation for barium phosphate actually results in 5 separate ions, 2 phosphates and 3 barium 2 pluses. And so my stoichiometry is not 1-to-1-to-1 anymore, which means it's the return of exponents in my K equation. Right. Other than that, this should still be old familiar ground, right? It's not 1-to-1-to-1 anymore, but it's 1-to-3-to-2. So minus x plus 3x and plus 2x. I plus c is still e, right? And the stoichiometry becomes the exponent in the K equation. So the KSP is the barium cubed times the phosphate squared. And so in this case, I'm going to end up with an x to the 5th term. Right, and this is not uncommon to get now higher orders of x, because if I have any salt that's not simply 1-to-1, I'm going to have 3 or 4 or 5 pieces. And if I have 3 or 4 or 5 pieces, I'm going to have 3 or 4 or 5 in the exponents. Right. Right. So to go from here to here, I need to take the 5th root. I remind you, depending on how unfamiliar or familiar you are with your calculator, there's 2 different ways typically on your calculator you can get a 5th root. Right. One is to raise it to the 1/5 power. Right. So if you have a caret function, any number raised to the 1/5 power is the 5th root. If you want the 4th root, it's raised to the 1/4 power. If you want the cube root, it's raised to the 1/3 power. There is also frequently an xth root button on your calculator, where now this would be 5 in this case. You might want to play with that just because sometimes the order of operations is slightly different, right? Whether it's 5 xth root number or number xth root 5 can vary a little bit from calculator to calculator. And so if I do that, again, I get a number which represents the solubility, because on this side, it's always just X, which is the amount of the salt that dissolves. And so X is always the quote unquote solubility. And again, I just need to be a little bit flexible with the units, because it does get expressed more typically in some version of grams per unit volume, right? But again, that's just a molar mass conversion. If I want grams per liter instead of moles per liter, right, the molar mass of barium phosphate is 602 grams per mole. That's one of those sort of editorial changes in units, right? But this is probably the Wikipedia number. But again, not to belittle my 25-minute effort here, right? I rarely want to do this calculation, right? Because it's always going to give me the same number, right? And so there's not a lot of point in using KSP as the reference for solubility. If I'm just dissolving a salt, I might as well just use the result of the calculation, which is why if you go to Wikipedia, under solubility, it tends to give you the number, the concentration itself, not the KSP that was used to solve for the concentration. The reason I even care about KSP is not so much the solubility, although again, that's what it represents, but it's the reverse process, which is the precipitation. Right. Now, I could write the precipitation as literally the reverse reaction, right? It's barium and phosphate ions coming back together to form now an insoluble, right, excess of salt, right? Because KSPs are a thing, I almost always write the reaction this way, even if I'm trying to do this, right? Because the K is specific to the reaction. I could invert the K and reverse the reaction, but there's no real benefit to that. Right. Right. And so, right, the simplest version of the precipitation is I dumped a whole lot of solid in there, too much solid for the solubility, and the excess has to precipitate, right? In the end, that's not going to be the problem I want to solve, as you'll see, but it is the basic of my precipitation, right? My solubility is the maximum amount that will dissolve. If I try to exceed that, right, the excess has to precipitate, right? And so that could happen, but it will only happen if I exceed the KSP, right? And so I mentioned before, there's sort of a fourth step to my KSP problems, and that really is trying to decide if I even have a K problem to solve, right? And this test could be applied for either solubility or precipitation, right? But again, my solubility number is generally known as just a number. The precipitation, as you'll see, is a little more complicated, right? And the issue goes back to, right, what my K equation is, right? It is the product of the ion concentrations. And specifically, right, it's the maximum amount that will dissolve, right? But again, it's also the minimum amount that gets me to equilibrium. Right? This is the first reaction type we had where I am not mandated to find equilibrium, right? And so, unlike before where it's automatically balanced equation, K equation, or ice chart solve, because I always get to equilibrium, here I could save myself some trouble by upfront deciding whether or not I really even have to try to get to equilibrium. Right. And again, this is only because of the absence of the reactants in the K equation. It doesn't know how much solid barium phosphate is there, if any. As a result, I can have 0 reactants left, which never happened for a Ka or a Kb. Right? Here it could, right? And it could happen long before I get to the actual equilibrium value, right? If I sprinkle a very little bit of barium phosphate in a gallon of water, it all dissolves, right? But I'm not at equilibrium if the product of those ion concentrations doesn't equal the magic number, right? I am allowed to be below the equilibrium, right? And so here's the only time I really need, well, I shouldn't say that. Here's one of 2 times I actually need Q, right, which we flashed by earlier in equilibrium, right? Q is just the K expression when I'm not at equilibrium, right? Technically, my equilibrium expression is barium cubed times phosphate squared, but again, it's only a equilibrium expression if I'm at equilibrium. In other words, if the product of those concentrations is 6 times 10 to the minus 39. On the other hand, right, I can have whatever barium or phosphate concentration I want to throw into a bucket of water, right? If it's not 6 times 10 to the minus 39, it's still a number. It's just not the equilibrium number, right? And so this is frequently abbreviated as Q. And it's really just a way of knowing where you are relative to equilibrium, right? Depending on what you were using as source material for the other equilibria, a lot of questions, I mean, probably some of the OWL questions asked, you know, whether the reaction had to go left or right to get to equilibrium, right? And that was a Q question, right? If Q is too small, right, in the normal scheme of things, right, too small means I don't have enough product. Or if you prefer, it means I have too many reactants. But either way, the solution to not having the right ratio is achievable by turning my reactants into products, right? The numerator goes up, the denominator goes down, I get to equilibrium. And so one of the ways people tend to use Q up till this very moment is really just as an indicator whether the reaction needs to go to the left or to the right to get to equilibrium. I personally never care about that, right? For my other reaction types, I always get to equilibrium. The math will take care of that. I always go plus x minus x, and excuse me, I always go minus x plus x and plus x, because I'm always essentially assuming the reaction goes from left to right. If it's really going from right to left, the answer will be a negative x, right? but I don't need to know, so there's no need for me really to calculate that most of the time. Right. There is a reason to do it here, however, because unlike before, I don't have to get to equilibrium, right? So if I calculate my Q, right, and my Q is too small, right, it means I'm not at equilibrium, and my only path to equilibrium is to, again, turn reactants into products, right? If I'm too small, this needs to get bigger, and technically this needs to get smaller, but for a KSP, I don't see this. Which is why there is no pathway for me to get to equilibrium if I don't have any solid left, right? This is where the invisibility of the reactants causes the problem, right? In a Ka reaction, there's always a little reactants left. I can make K bigger or smaller by just having a little bit more or a little bit less of the reactants left over. If I have no reactants left, right, I don't know it. My Q doesn't become infinity because the denominator is 0, because there is no denominator. The denominator is always 1, right? And so if Q is less than K, I'm not at equilibrium. But in the case of a KSP, it also means I can't get to equilibrium if I don't have any more solid. Right. And so my Q test tells me I have nothing to do here, right? I've got dissolved ions, yay. I have a solution of a certain molarity, yay. I'm not saturated, yay, but there's also nothing left for me to do. I can't become saturated unless I add more solid, and I don't necessarily have any more solid, right? On the other hand, if Q is greater than K, right, I'm still not at equilibrium, right? The pathway to equilibrium is now right to left, because it's still products over reactants. Although, again, for a KSP, I'm not seeing this, right? But I do have products, and I can do the reverse reaction. And so if Q is greater than K, right, I'm not at equilibrium, but I do have a pathway to equilibrium, which is to precipitate the excess ions to get me below the solubility maximum. Right. And so for a typical precipitation problem, I sort of add the Q test. Right. I'm still going to need to write out a balanced equation because I always need a balanced equation. I'm still going to need a K equation because that's where my Q comes from also. But I'm not necessarily going to just start by making an ice chart, because unless it passes my Q test, there's no equilibrium to solve for, so there's really no point in an ice chart. Yes, no, maybe? And here's the thing about my precipitation that makes this an actual equilibrium worth considering, right? If I'm just taking solid barium phosphate and dissolving it, right, again, I just have a solubility number that I can't get past. And I'm either at it or below it, right? It's a very, at that point, binary situation, right? If my solubility is 10 molar and I'm 3 molar, I'm not at equilibrium. I'm also happily not at equilibrium because there's nothing I can do about it, right? And if I try to dissolve 12 molar and the solubility is 10 molar, it simply won't dissolve, it'll dissolve to 10 molar and I'm done with it. Right? And so the pure solubility or even the pure precipitation problem is kind of boring and not worth considering. Here's a case where Wikipedia, right, is the shortcut that actually is worth pursuing and makes my life easier, right? Because it is just a point in space, right? If I'm trying to dissolve a salt, there's a maximum. I can be under it, I can be at it, I can't be over it. There's really not a lot of point in doing some fancy math to prove that. Right. But where the precipitation becomes an equilibrium problem that needs to be solved is when my ions don't all come from the same source. Right. In other words, if I am mixing solutions together that might be perfectly fine by themselves, right, I suddenly have more ions that are seeing each other for the first time. In that case, I might be exceeding the solubility limit for a salt I never had. KSP every year is the thing people get wrong the most frequently. Right? Because it is so different than the other equilibria, and also because it defies your student expectations that were, again, ruined in high school, right? That what matters is what you see, right? Here I have iron nitrate and potassium hydroxide, and I mix them together. It may surprise you to know that I don't care at all about iron nitrate or potassium hydroxide, and this problem has nothing to do with either one of them. Right? Because the iron nitrate is dissolved. How do I know? It's a 0.1 molar solution. If it wasn't dissolved, it would be a lie to call it a 0.1 molar solution. What's the solubility of iron nitrate? I don't care. I guarantee it's more than 0.1 molar. How do I know? If it weren't, I wouldn't have a 0.1 molar solution of iron nitrate. Same with the potassium hydroxide. I don't know what the solubility of potassium hydroxide is, but I guarantee it's more than 0.1 molar. Otherwise, my solution is fictional. And when I mix them together, they just get more dilute. Right? I've essentially added more water to my iron nitrate. So if it was all dissolved before, it's still dissolved. And my potassium hydroxide got more dilute because I added more water to it. And so if it's dissolved, it's going to stay dissolved because it's even more dilute. And so this problem is not at all about iron nitrate, and it's not at all about potassium hydroxide. They are dissolved. They will stay dissolved. Their solubility is not in question. Right. On the other hand, right, if I mix those two solutions together, the iron and the nitrate are happily below the solubility. The potassium and the hydroxide are happily below the solubility. On the other hand, iron has never occupied the same beaker as the hydroxide previously. Whoops. All right. Similarly, the potassium and the nitrate have not occupied the same beaker previously. And so while I don't have to worry at all about iron 3 nitrate and potassium hydroxide, right, when I mix them together, it is possible that I do what in Chem 1 we were calling a double replacement reaction, right? And it's possible that the products I form, right, are less soluble right, than the ion concentrations before I mix them, right? If iron hydroxide is not very soluble, and it isn't, it was never an issue before because there was no iron and hydroxide in the same beaker. But now when I mix them for the very first time, the iron and the hydroxide are in the same beaker. And now there's a real question as to whether or not the ion concentrations are above or below the maximum that's allowed, better known as the KSP, right? And so, again, chemistry in the end always boils down to opposites attract, right? The potassium could associate with either of the negative ions, hydroxide or nitrate. The iron, a cation, could associate with either hydroxide or the nitrate, right? But again, the two things I started with are not at all worth considering. They were dissolved when I started. They're more dilute now. They're clearly not going to precipitate, right? But this is the first time the iron saw the hydroxide, and it's the first time the potassium saw the nitrate. And so it's possible the ion concentrations are too high. Right. And so what happens depends on where I am relative to KSP. The other thing that's a little bit backwards about my precipitations is I've been harping on biggest K, biggest K, biggest K. This is still true, except, right, if I'm precipitating, I'm going backwards. So the biggest K precipitation goes with the smallest KSP. Right. And so if something's going to precipitate, the first thing I'm going to look at is the smallest KSP, because that would be the biggest K precipitation. Right. If you look up potassium nitrate, I didn't actually put the number on the slide. I think if I recall correctly, the number is 714. Right. As you might expect from our oversimplification in Chem 1 and or high school, potassium salts are soluble. Nitrate salts are soluble. Potassium nitrate is very soluble. Right. And I believe 714 is the actual KSP. On the other hand, iron hydroxide, iron 3 hydroxide, the KSP is only 10 to the minus 39. Right. Now, again, it is theoretically possible that the potassium nitrate could precipitate. Right. It's theoretically possible that the iron 3 hydroxide could precipitate. It's also possible that neither one precipitates. It depends on where my Q is relative to K, right? For the potassium nitrate, right, my Q, worst case scenario, was 0.1 and 0.1, right? My Q is 0.01. It's way less than 714, right? Meaning potassium nitrate is not at equilibrium, but it's below equilibrium and it can't get to equilibrium. And so I ignore it, right? On the other hand, in round numbers, again, I have to do the dilution, right? The QSP really here is essentially 0.0001, which is way bigger than 10 to the minus 39, right? And too big, still not at equilibrium, but too big can get to equilibrium by precipitating. And so we will solve that precipitation problem on Wednesday. So it's not to go 1 minute longer. I did see, was it Nadia's question in the chat about postponing sprint 4. I can postpone sprint 4, but sprint 5 is going to be 1 week after. And so since I don't really care and I still have 197 project 2s to read, fine, I will make sprint 4 due next week, but keep in mind sprint 5 is going to be due the following week because we're going to soon run out of weeks otherwise. Questions or problems? Then happy Monday.